Welcome to another lecture on the Internet of Things. We are currently discussing data in the IoT, and in the second lecture on data, we are going to talk about data formats. So, you see the diagram again that we've already seen in the previous lecture, and we've already talked about common network formats. We've talked about how to acquire sensor data, how to fuse sensor data, and all the signal processing artifacts that might appear. But we haven't talked about how we would be able to actually communicate all our sensor data effectively and interoperably in such a large heterogeneous network as the IoT builds. So the challenge here today is to find a common language to communicate between vastly different nodes in IoT systems. So we've already seen this IoT networking overflow before, and we've seen that essentially for many IoT applications, the three lower level on the right-hand side for a TCP/IP-based network. So the network hardware layer, the network transport and transport layers are essentially unchanged. So for very many applications, really run a given hardware and wireless network protocol like 802.11 for wireless networks. And on top of this, we run IP on the network layer, so IPv6 or IPv4. And on top of IP, we have a transport, which is commonly either TCP or UDP. Now, we've also seen that just using TCP and UDP itself is problematic for many of the communication patterns we want to enable in IoT systems. So on top of our transport, which is on the application layer, as seen on the right-hand side here, we have some common protocols that enable IoT systems to exchange data in an effective way over whatever protocol and TCP IP they are implementing. And so we've seen examples for MQTT, MQTT-SN, and different other protocols in the infrastructure part of that course here. Now, MQTT and others now solve the problem of addressing things and distributing information in IoT-based networks. So we can have an easy way to find information, to distribute information, to indicate that we are interested in some information. And the problem is now that this only covers the distribution of information, but not what the information itself looks like. So a more precise challenge that we have to solve here is that MQTT and other middleware protocols for networking IoT systems do not define the formats for data that is exchanged between IoT nodes. So we have to do something about this. Let's take a look at data exchange in MQTT messages. You've seen a bit of this before if you have subscribed to the infrastructures lecture on networking. So MQTT, as one of the most widely used protocols for IoT applications, has very simple messages, and they consist of 4 parts. So we have all these parts relevant for actually getting packets from sender to receiver, or in MQTT case, from a publisher to a subscriber. And we have all sorts of meta or administrative information, like a packet length, information about the quality of service of a package, and so on. And finally, we can also already identify which subject or topic, as it's called in MQTT, a certain packet belongs to by looking at a topic. So a topic in MQTT, as we've already mentioned, is just a long UTF-8 string. And this UTF-8 string, similar to a path name in a Unix system, consists of names, which are UTF-8 strings. That can also include special characters or emojis or whatever. And they are sorted in a hierarchy. So we have an example here of my home. So I have an IoT network for my smart home applications, for example. And my home is then split into several units. And one of the units is called ground floor. And in the ground floor, I have several rooms. So, for example, a living room. And in the living room, I have a temperature sensor. So this makes a topic hierarchy of my home / ground floor / living room / temperature. And we've also seen that you can subscribe to subsets of uh, these topics instead of every single topic or sensor at once by using so-called wildcards, like using wildcards in file systems, though it's a bit more constrained. So IoT devices can publish and subscribe to messages about given topics, but these are the first three parts of the packet we show on the lower right-hand side. The remaining question is what's actually the content of the thing on the right-hand side, which is called payload. This obviously is the data to be exchanged itself between nodes in the IoT. So we have already seen this very simple data exchange, and there is no real standard describing which format data has to have when IoT nodes want to communicate. If you look at our network message diagram on the right-hand side, you see these boxes with the arrow on the side describe the publishing or subscription to certain amounts of data. And for each publish message, you see there is a topic like temperature roof on the top right-hand side, or temperature / floor in the middle on the left side, or temperature / roof again on the lower right-hand side. And we also see something else, which is the actual data transmitted. And here you see this is kept very abstract or simple. It just says, for example, 25 degrees centigrade, or 20 degrees, or 38 degrees centigrade. So this is our actual payload, the information in this system here about the actual current temperature at this given sensor, which is assigned to this topic we're talking about. This is like 20 degrees centigrade. Now the question really is, how do we actually encode this information that it's 20 degrees centigrade in the MQTT payload? And as you guessed, we have a number of options for this. So this is our challenge in detail. How do we encode such an arbitrary information like 20 degrees centigrade in the payload of an MQTT message? Well, in general, we can distinguish between two different approaches. One approach is a textual encoding. So we just take these characters of a message we want to send, so 20 space the degree character and the capital C for centigrade, as characters in an ASCII string. That sounds pretty useful because obviously ASCII strings are already used for the topics, or precisely UTF-8 strings, but let's look at ASCII strings before. So for each of these characters here, so a character with the digit 2, a character with the digit 0, a space character, and so on, we can look up the respective hexadecimal encoding in an ASCII table, and then we see, okay, a digit 2 has the hexadecimal value in ASCII of 0x32, a digit 0 has the hexadecimal value of 0x30, a space character has the hexadecimal value of 0x20, a degree character has, a degree character is not encodable in ASCII because in regular 7-bit ASCII there is no encoding space for a degree character. Okay, so ASCII strings might already be a bit difficult for our example here. Well, we can always switch to UTF-8 strings, which has a much larger choice of symbols to use. So for regular printable characters, UTF-8 encodings for values less or equal to 127 in decimal or 0x7f in hexadecimal are identical to ASCII encodings. So for 2, 0, and space, we have the same encoding as before with the ASCII string, and then we can actually find a character, or what's called a code point in UTF-8 for this degree character. And this doesn't fit in 1 byte, so we need an extension byte. So this would be the 2 bytes OXC2, OXB0. And then finally, we can find a regular uppercase C character at OX43. Now, all we wanted to send is a number 20, right? Now, instead of a number 20, we send 6 bytes already. So this creates an overhead for generating this data, obviously an overhead for transmitting this data if we send 6 bytes instead of 2 bytes, and of course also an overhead on the receiving end, because in many cases you want to work with this information again as a number, so you have to transform it from this ASCII representation back to a numerical representation. So you have to parse this information, check for correctness, and then finally translate it. And that's quite a bit of overhead. In addition, a text format can introduce a number of ambiguities. So, for example, one vendor might decide that, oh, well, I don't need that space before the degree character, so I can leave it out. Now, this can create a number of problems because if a receiver on the other end, so a subscriber, expects this space character to be present and finds the degree character immediately after a digit instead of a space character, it might not be able to understand the message or just outright reject it because of incorrect formatting. Well, there's another option. To be more efficient, you can simply send the data as binary numbers. So, for example, you could just agree between all the systems involved in your temperature processing on IoT that to send a temperature which has the value 20 degrees, just send a byte that has the value 20 in decimal. Well, that sounds pretty good at first because we only need to send one byte. That's quite nice. And it might work relatively well for positive temperatures at least, right? What do we do with negative temperatures? So can we send a byte -5 degrees? Well, we'd have to agree on a common number format, for example, 2's complement numbers. But then we have additional problems like, what do we do with fractions of a temperature? So how can we send the information it's 20.5 degrees centigrade? Well, we'd need to use yet another number format, like fixed or floating point numbers. And again, both communication partners have to agree on this. And then, of course, just sending 20 is maybe, also ambiguous again, because you don't indicate which unit system you're working with. So maybe you want to combine a European and a US American device, and your European device sends temperatures in centigrade, whereas your US-based thermostat that controls your heating expects temperatures in Fahrenheit. And so you send the information, oh, it's a cozy 20 degrees inside of my room, centigrade obviously, which your US thermostat controlling your heating interprets as, oh my, it's freezing cold, it's only 20 degrees Fahrenheit, so let's turn up the heating until it's really, really nice and cozy. That's not a good idea because in the end you don't want to have like 75 degrees centigrade in your room. So we have a lot of problems here. Like we can have different formats for binary numbers, integers with or without negative values, fixed or floating point numbers. We haven't specified any units. And in case we want to send larger numbers that don't fit in one byte, as integers, for example, we have to define things like byte orders. So in byte orders, you have two different approaches, which we call big and little endian. So when a word consists of, for example, 4 bytes, then you can put them in one of two orders. So big endian means that the most significant bits of your value come first, so are the first to be transmitted, whereas little endian is just the other way around, so the least significant bits, so bits 0 to 7, are transmitted in the first byte, and then it goes up until you reach bit 31. So both approaches are not ideal. Binary number encoding has very many ambiguities and problems. Textual encoding has overhead and also ambiguities. Now, we need to find a way to make this work easier with like a large number of systems. So what we want to have is a common data format for IoT applications. This should be common, flexible, and improve our interoperability. We have to pay a price for this, and the price we have to pay for this is we will definitely have to pay some overhead due to enabling generality and enabling more context or semantic information to be transmitted with such a common data format. One common data format that was proposed for all sorts of data exchange is something you've probably seen before. This is XML, the Extensible Markup Language. XML is in general, a generalization of things like other markup languages you might know. So the idea was originally with SGML, the Standard Generalized Markup Language, which then influenced HTML, the hypertext markup language, and XML in general is pretty much a generalization. So if you have written web pages by hand using HTML, you know the notation already, so you have some items in these angle brackets or less and greater signs, and some data in between these items. So XML is what we call a markup language, so it describes, well, originally the metadata for your information. It can be used for transferring data and also, of course, for storing and reconstructing serializing data. XML defines a set of rules for encoding documents, and the idea of XML was that it should be a format that's both human and machine readable. Now, if you've looked at a complex XML file before in your life, you notice that might well be machine readable, but it's quite an overhead because you have recursive structures, for example. So you can't just work with regular expressions for parsing them. You need a real parser. And it's not very human readable, especially for more complex documents. In the end, the overhead for using XML is rather high. For example, if you want to parse it correctly, you have to invest quite a bit of code, quite a bit of effort. So what we would like to ask ourselves is there maybe an easier solution that's a bit more simple? And this was introduced in the context of JavaScript development, actually, and it's called JSON. So JSON stands for JavaScript Object Notation. Like XML, it's a language-independent data format, even though JavaScript is part of the name because that's where it originated. And it's a bit more lightweight compared to XML in IoT applications. There are certainly some IoT applications using XML, but JSON, I think, is the standard that proliferated more and might be the more interesting one. That's why we discuss it here. So JSON, like XML, is an open standard as a file format and also as a format for interchanging data between nodes. Again, the requirement was to have human-readable text to store and transmit data objects that should still be easy to parse and understand for computers. And the general idea in JSON is that data objects consist of attribute value pairs and arrays of these. In general, JSON text is a sequence of what we call tokens, and these tokens are again formed from Unicode characters, or precisely Unicode code points. And we have a so-called grammar that we require every JSON document to adhere to. So a grammar gives you the structure of a document in JSON. And if you write a JSON parser to understand JSON, or if you write a JSON generator, you need to implement the rules of this grammar. So here we have an example for a JSON file on the right-hand side. So you can already see some of that stuff is readable. And we've color-coded some of that things. So the outer red line indicates a large object. So this might be one data set for a person here. So we see the outer characters in our example here are curly brackets, and objects are always delimited by these curly brackets, so an opening and a closing curly bracket. Inside of this we have elements, and these elements themselves are separated by commas. We can nest objects into other objects. So for example, we see that the yellow background text here is again between two curly brackets here. So the address information, so that just makes up another object, which is part of our outer object here. Well, the important base structure of a JSON file is what we call a key value pair. That's the thing with the blue outline here. So a key value pair is something that has a colon in the middle, and the left-hand side of a key value pair is what we call a key, and the right-hand side is a value assigned for a key. So this is very similar to databases where you identify information according to whatever you can tell about their semantic relevance. So for example, the highlighted thing here would be first name. So we have a data set for a person, obviously, with a first name of John, and we have a last name of Smith. We have some other properties. We see it doesn't always have to be strings, so is alive. has the value of true, so which is a Boolean value, just well, which is just able to have true and false as values. We have a key called age, which has a value of an integer called 27. And then we see we have a key called address, and address itself has another object as its value. And the final thing we see, which is with the light blue background, is that we can also have arrays. That's what you see attached to the phone numbers key as value. So these are using these square brackets. And these square brackets, like arrays in C or Java, just denote the limits of our array here. And inside of that array, we can have several elements, again, separated by commas. And here we can have, again, different objects, type and number. So we can have a home phone number and an office phone number inside of this. So this might remind you quite a bit of struct syntax and array syntax in C and Java, and this is probably intentionally done so because JavaScript also uses a C-like syntax here. So this is something that's very, very similar and very common to use if you've programmed in C or Java before. You can also have some special cases like an empty array for the second line to the last, which is children. So you could have an array of children, and if this person, John Smith, has no children, we can obviously pass an empty array, which just consists of the opening and closing square bracket. And John Smith doesn't seem to be married, so there is another key called spouse, and spouse is not referencing to any single entity, so it's just null. Null means there is no information provided. So this is just an example which shows the most important parts. If we want to get a bit more formal, we can dig into this again a bit more in more detail. So first we should ask ourselves which data types can be used in JSON files. And we've seen a number of examples for this. So we've seen numbers. Numbers are signed decimal numbers. They can be integer numbers, but they may contain a fractional part. And for scientific applications, they may also use the exponential e notation, like 6.023e something. But they are not allowed to include non-numbers. So if you know about floating point programming, you know there are special number representations which indicate that a value is not representable as a number. For example, if you try to divide by 0, your result would be something we call a nan, not a number. This is representable in a standard floating point format like IEEE 745, 754, but not in a JSON number. We've also seen strings, so a string is a sequence of 0 or more Unicode characters or code points. We've also seen strings, like we are used to, are delimited with double quotes, and if we need a double quote inside of a string, we can use a backslash syntax to escape that double quote, so we can insert a double quote character inside of a regular string. We've also seen Boolean values, which can have the values true or false, and we've seen collections like arrays. Arrays are an ordered list, and we see they can contain 0 elements or 1 or more elements, and each of this may again be of any of the allowable types, like for example, we can have an object again inside of an array, and these arrays use the square bracket notation with comma separated elements we are pretty much used to for arrays from C or something. Finally, we can have objects, and objects are a collection of name-value pairs. You can see them as similar to like a struct in C, and the names or keys are strings, and for these strings, there is no restriction as to their format. So JSON does not require that name strings are unique, for example, and it does not assign any significance to any ordering of the name and value pairs. So you can put them in any order you like, as long as they are in the same object, for example. We've also seen objects are delimited with curly brackets or braces, and they use commas to separate the pairs. And within each pair, this colon character then indicates what's to the left of it is a key, and what's to the right of the colon is the value. And finally, we can have null, which is an empty value, which just has the special reserved word null. Now, JSON files can be a bit more free format, so we've seen there's a lot of what we call white space in there. So in addition to these special characters we've already mentioned here, so the opening and closing curly and square brackets, the colon and the comma, we don't have many reserved characters, so we only have three literal name tokens. We've already seen true, which is just a sequence of the Unicode characters for T, R, U, and E, and the same for false, which we haven't seen, but which you can probably imply what it means, and for null. So this is just the ASCII or Unicode UTF-8 characters for these strings which are used. And finally, everything else in between is what we call white space. So white space is not relevant within a JSON file. So if you have programmed Python before, you know white space can be very relevant for indicating indentation for loops or if statements. In JSON, people thought this is not a good idea, so white space is usually insignificant. So it's allowed before or after any token. So if you have a colon or a comma somewhere, you can put it directly. For example, you can directly put a colon between a key and a value, or you could add a number of spaces in between here. So what's a white space? Now, a white space is defined as anything that's not printable. Now here we constrain it a bit because UTF has quite a number of code points which don't result in any printed output because there are so many separate versions and variations of space characters. So JSON constrains this a bit. So for JSON, white space that's allowed is any sequence of one or more of the following code points: the tabulator character, so that's what you get when you hit the tab key on your keyboard, line feed and carriage return, and the regular space character. Within a token, white space is not allowed, except that if you want to use a string, then spaces are allowed. So if you have something in between double quotes, then you can freely add spaces there. And this is the only case where spaces or other white space becomes relevant in JSON. So one question we should ask ourselves is like, okay, now we have a general idea of what every JSON file has to look like, but for my specific application, I still want to describe like what are the valid objects, what are valid formats, what are valid keys, valid values, or value ranges, for example, inside of a JSON file for a certain application. And JSON enables us to define and validate this information by using JSON schema. So a JSON schema is what we call metadata, so data about data. And it specifies the format to define the structure of data that's allowed within a specific class of JSON files. For example, the class of JSON files you want to exchange between your IoT nodes. So JSON schema defines the structure of a JSON element and additional properties like which keys are valid, which data types are used for values for which keys. We can use them for validation, for documentation, for interaction control. They're again human as well as machine readable. And the interesting thing is that we're a bit recursive here. So JSON schema itself is based on a JSON notation. So it's all a complete package here. So we can also say that JSON schemas provide a contract for the JSON data required by a given application and also informs the application about how that data can be modified. Let's look at an example for a JSON scheme here. So this is an example for like product catalog entries. So if you're running a shop selling things, you need a product catalog with information like the name of a product and the price of a product and maybe some unique ID like a EAN number, which uniquely identifies your wares. So you can identify them, for example, with a barcode reader. And this is a basic JSON schema defining these product catalog entries. So the first thing it starts, you see it's an object, it's contained in curly brackets, and it starts with metadata about the JSON schema. So it says $schema. There's different versions of the schema specifications. So here it gives the URL that informs to which version of the schema specification this schema actually conforms to. Then you can give it a title and a longer description. So the title would be product here. A description would be something for humans probably to read like a product from a catalog of our company Acme. And it has a type, and this type is object. And now we can say objects in a JSON file that conforms to this schema have certain properties. And these properties might be we have an ID inside of this, and again we have a human readable description, so the unique identifier for a product, and we do prescribe that whenever we have an ID, the value that's assigned to this ID in a JSON file must be of type integer. And the same for name, so the name of the product must be a string, and the price of a product must be a number. We can set a minimum price here, for example, of 0, and we can also say that we want to exclude the minimum of the price because we don't want to have products that have a price of 0. And so this gives the structure of all fields that are allowed to appear in such a JSON data set for our product catalog. And then the question is, of course, do I need just a subset of them or do I need all of them? So I can also have an attribute like on the last line here, required, which is an array again that informs whoever is processing this JSON data, like which of these elements are required, so which of the keys are required to be present. And here we say that all three, ID, name, and price, have to be present in our JSON file, of course. Right. So a very simple JSON data set that conforms to our specification here looks like we see on the right-hand side. So here we have two data sets, so they're contained in an array, and each array element then has to conform to this JSON specification here. So we have two array elements, so two product entries. The first one has an ID of 2. We see it's a number, so it's perfectly valid. It has a name, which is a string, a nice sculpture, and it has a price, which is a decimal number, which is not 0 and is not negative, so it's 12.50. And we have another product with an ID 3, which is a blue mouse with a price of 25.50. So using this schema from the previous slide, we can easily verify that this is actually a valid JSON dataset that conforms to our product catalog schema specification here. So of course, we should ask ourselves, is this really used in IoT applications? And of course it is. So I've brought you an example here from a family of sensors by a company called Advantech, which are called Wizard without the I. Yes, that's not a typo. And these sensors on the network level communicate using MQTT. And the payload in this MQTT protocol packets contains data in a JSON format for all the data being sent across the sensors of our sensor network. And in this datasheet, we've linked under reference 4. There's a number of examples for all valid JSON data. So for example, we have an accelerometer sensor here, and here we give the MQTT topic. So the MQTT topic consists of the vendor ID, which is BB in this case. Then, as we mentioned in the MQTT topic discussion in the infrastructure section, we usually have some unique identifier for a sensor. So if we have 3 or 4 or 5 sensors of the same type, we would still be able to distinguish from which sensor a certain data set came. So for example, this would be just a long hexadecimal string indicating maybe a serial number and then /data. So whenever an MQTT topic is posted with exactly that value here, then the payload of that MQTT is expected to have the form that's shown in the third column here. So this is example JSON data, which has information S, whatever is S, we'll see this in a bit. T, well, we can imply what T might be, that's a timestamp, and we've talked about time in systems before. We have Q and C, we don't exactly know what this is, but if you look at the additional data sets here, you see, oh, they seem to be appearing in all of the data sets, so there's something common in them. And then we have specific information, like for the accelerometer, we have information about the 3 dimensions in space, so the displacement of the accelerometer in X, Y, and Z dimensions. So you see that there are nodes for these specific data elements on the right column here. So X, Y, and Z as the X, Y, and Z axis values. And it also gives information about the format. So it will be 4 digits, a decimal point, and possibly a negative sign. And we have something similar for a temperature sensor. So a temperature sensor then gives 2 temperature values here in configured engineering units. So you see something here. If you don't want to agree on a certain format like temperatures in centigrade or kelvins or Fahrenheit, then you can actually configure a sensor to deliver data in the required format. And since we have something like minus 273.0 here, which is almost absolute zero, we should be able to assume it's centigrade in this case, but you could reconfigure your sensor sending configuration messages. And we can also have some voltage supply information. So here we have VBAT, so the battery voltage of 3.1 volts indicated. And there's a large number of additional messages, of course, which are all listed in this datasheet we've linked. So if you want to use these sensors and if you want to integrate them, you have to read the datasheet and you have to prepare, if you subscribe to messages from these sensors, you have to prepare to parse these messages and then make use of the data. So of course, we also have a schema for this information. So again, as we said, this is a specification for the data format published by the devices of the Wizard sensor family, and this is published by the manufacturer. So we already see it's a schema that conforms to this draft 04 schema of JSON. The title is sensor data, and we have some description for humans to read. Its objects, it doesn't have additional properties, it has some required entries, S, T, Q, and C. And here we have some explanations for these properties which just had a short name, which is very useful to have these short names because you can save on transmission bandwidths by just having short, unique names. And here you can have an explanation. So S might be a sequence number, which is just incremented. So whenever you send a new set of data out on the network, you just increment that number. And we see it's type integer. It starts at 0, it ends at 9. This is not a lot. We have timestamps. Timestamps is our string, but we can actually require this string to have a certain format, which is date time, which is a standard ISO 8601 timestamp, and it's UTC, so you don't have to care about things like time zones here. Then you have some quality code. So the sensors can indicate what the quality of the reading is, and this is just an integer between 0 and 255. And we might have a configuration index. So like when you do reconfigurations, maybe the sensor takes some time to adapt to this reconfiguration. So if you number your configurations, you can figure out that a data set that arrives still belongs to your previous configuration. So when during the operation of a sensor you decide to switch from centigrade to Fahrenheit, you would still be able to figure out which of these subsequent messages arriving would still be in centigrade instead of in Fahrenheit. And then we have all the additional information here that might occur, like X, Y, Z for our accelerometers. We have analog input values and a lot more. So we're only showing the first like 20 lines of that file here, and it's quite a bit longer. And if you're interested, you can read it in completeness in the linked datasheet. So we've seen at the beginning that we can have the general choice between binary formats, which are hard to handle, and text formats, which can create ambiguities. Now, JSON can reduce these ambiguities quite a bit by requiring formats, value ranges, having numerical formats, having strings, having just explicit information about true and false, and also indicating null values when nothing is present. So that makes it quite a bit more convenient to use. But of course, we have more overhead because now we have a structure to parse, we have keys, which have to be transmitted along with data, with the values, and so on. So JSON implies a storage and bandwidth overhead. So the overhead, for example, through the inclusion of keys and also the structuring characters like brackets and commas, whereas binary data could just simply use fixed offsets in a data packet. So we'd say whatever temperature is always at byte 3 of our payload, and at byte 4 there's some other information without indicating any separators between the data. For strings we want to send, there is no significant overhead because the only overhead is just the delimiters, the double quotes we have to send along, and these are and the structural elements. So these are relatively low overhead compared to long strings, but there can be a significant overhead if you just want to send numbers. And for an example is you want to represent the value of pi here with like 7 significant digits after the decimal point. So there's a standard for a floating point number representation. It's called IEEE 754. And this would imply that a single precision floating point number, which can have like up to 7 significant digits after the decimal points, takes up 4 bytes. So this is a format that decomposes a floating point number into an exponent, a mantissa, and a sign bit. And you can also have double precision floating point numbers, which can have more significant digits. These usually take up 8 bytes. Now, if we want to represent 3.151415926 as a UTF-8 string, we need the 9 characters making up the number, including the decimal point. So these are 9 ASCII characters or UTF-8 code points. Then we have 2 delimiters. We have to put around this somewhere. So we have to transmit at least 11 bytes compared to 4 bytes as a number. So this is quite some overhead, and depending on your application, you might be able to afford this overhead or not. For very small microcontrollers in the IoT, which only have like little memory of like less than a kilobyte, and these are the cheapest controllers you want to use in cost-sensitive applications, maybe still you want to use a numeric binary representation of values, just because otherwise you'd be running out of memory and possibly computing power when you have to process a lot of data. And of course, we have a processing overhead, so usually the data we receive from sensors is received as numbers, so as integers, fixed or floating point numbers. So when we want to publish them, want to send them out over the network, we have to transform them into this text format here. We have to store this JSON schema or write a program that creates this JSON schema somewhere. We have to have the buffer space for this. We have to send it out. And of course, on the receiving end, at the subscriber, usually all this process has to be done in reverse. So all the textual representations for numbers, for example, have to be converted back to integer or floating point numbers. Now, of course, we are not the first people having this problem. So there are a number of efficient implementations of JSON generators and parsers for all sorts of languages out there. So you can actually, when you design an IoT node, choose which of them to use. It's usually not required to write your own JSON generator and parser. So what have we learned today? In addition to these message exchange standards we've seen before, such as MQTT, we also need information that describes how our payload, our actual data we want to process, looks like. So we need standards for data exchange. And we've seen that binary data is hard to handle correctly, especially if we have heterogeneous environments such as IoT systems consisting of devices from different vendors. We have different approaches. We've seen a bit of XML, and we had a detailed look at JSON. And JSON is, I think, the prevalent data format used for IoT applications that can afford to have the overhead. And we've seen that JSON is a structured, human and machine readable data format. It's based on Unicode, thus it's portable and flexible. It's relatively simple to generate and to parse. And we have the benefit of having JSON schemas that can be used to validate the correctness of a JSON file. So, of course, we can only validate the structural correctness, so syntactical correctness. We cannot validate the semantics, so we cannot validate if the values inside of that document really makes sense. We can just check if they're between certain limits. JSON now has significant overhead still compared to sending binary data. So when you design an IoT system, well, either you have to live with what the components you're going to use actually transfer and expect, or you have to write translators. For example, you could imagine that, essentially your broker could translate data formats between different nodes, which would require quite some overhead at the broker. And if you design systems from scratch, of course, you're free to choose formats, but of course, you can guarantee an increased interoperability when you actually use JSON format here. But of course, there are many choices out there, proprietary choices. Some use XML still, so it's up to you. So I thought I'd present you the most common approach, which is currently used in IoT here. So that's all for today. Thanks for listening. Here's a number of references about different ideas and especially about JSON and how it's used in IoT applications. So thanks for listening, and until next time, bye.